Okay, so in Newton's method, we realize we need to calculate Hessian. Oh, I made a mistake here. I need to do inverse here. So sorry, in the previous slide about the flow chart, I forgot about the inverse. Okay, so let me get back to my point. In Newton's method, you need to calculate Hessian, and then you need to do inverse, which is okay when your variable, when you only have two variables or three variables. But what if you have 10 variables? How do you solve a inverse matrix of a matrix that has a dimension of 10, 10 by 10? Then you cannot do it by hand. So that's why it's important to use computers to solve this kind of problems. But so people try to find other methods and see if we can avoid Hessian matrix. So I'm going to talk about this method, the steepest descent. Steepest descent. The idea is to avoid Hessian and its inverse. Can we avoid this? Okay, so if we look at Newton's method, if you look at this, here is a very important thing, which is the inverse Hessian. And let's look at the other guy. Here. What is a gradient? This is basically the gradient vector. It's a direction that shows how f decreases, or I should say how f changes its value with respect to the position of x, right? So a gradient is about directions. If you look at 1D, this is basically slope, right? So if I have this is a slope. Okay? And if I have a 3D, that's a 2D, let's say this is a f of x1 and x2, and let's say my coordinate system look like this. Okay, let me do this. Okay, and at some point, what does the gradient look like? It's a vector. Also showing you how the shape look like. So this is your gradient. and here is some point xa, and this vector is the gradient at xa. So it's actually the gradient vector usually is going up, so if you cannot imagine this, you can look at, let's say, f equals to x1 squared plus 10 x2 squared. Okay, so at some point xa equals to 1, 1, what is the gradient f? Basically is 2x, 20x, so it's 220. So if you try to visualize that, here is 1, 1. And what is 220? 220 looks like this. This is like a vector of 220. Okay, so that would be the gradient at 1, 1. And it's usually going toward the direction where function value increases. So how about the negative gradient? This is the direction of f decreasing, right? And remember, we want to minimize f. So we should try to move along negative gradient. And look at this. Newton's method is also trying to move along the direction of negative gradient. But Bayesian is there to change the direction a little bit. So Bayesian helps you to change the direction of the negative gradient, and it's derived from Taylor expansion. And when we use steepest descent, we don't have Bayesian. So what can we do? Now let me copy some of those and move on to the next page. Okay. So for steepest descent, actually the formulation looks very similar, but introducing a new coefficient we call alpha times gradient f. So the new component for steepest descent here is alpha. So alpha, sometimes we call this the step size. Why do we call it a step size? If you look at a 2D problem and we have a contour, and we know this is the minimum point, and let's say we are standing somewhere, and like I told you, the gradient usually is going to, so basically along this contour f decreases. Okay, but gradient, the vector of gradient is facing toward the direction of f increasing. So this is the direction of gradient at some point xk. Okay, so this will be the gradient of xk. So how about the negative one? The negative one basically going this way. So this is the negative f. So we should try to move along negative f. We try to move along negative f. Negative gradient, sorry, negative gradient. Negative gradient. But how far do we move? How far do we move? So here is a line. Here's along some line, along a linear direction. Toward negative gradient. So we need to know how far do we move along this line. And let's say we move up to here. We move up to somewhere here. So this distance is basically alpha times negative gradient, right? So by determining alpha, we can know where is k plus 1. So the important thing is how far do we move, basically what is alpha, along negative gradient, so that we eventually can find our optimal solution. That's the important question. That's basically what we want to do, right? How far? So we need to know how large is alpha, right? So when we introduce alpha, it becomes a new problem that we are trying to determine what is the value of alpha. Okay, so let's move on to the next page. Oh, by the way, do we have questions? Okay, so if you have questions, you can message me using the QR code. Okay. Oops. Paste. Okay, so when we do this, when we introduce this equation, it becomes a totally different problem. We are trying to find alpha. So how do we do that? We will plug in f. We will basically plug in f. So what do we get at the end? Basically, it's like this. We try to plug in. So in our function, we have our variable, and we try to use this new equation and then plug in, even though we still don't know alpha right now. We just plug in, try to plug in. Okay? Try to plug in. So what will happen is, because we already know these two, we have our previous design and we know the gradient. Only thing we don't know is alpha. So this function become a function of alpha. A function of alpha. the unknown alpha. Okay? So it become a finding alpha problem. Okay? Because alpha is just one value, so this become a 1D finding alpha problem or 1D minimization with respect to alpha. So it becomes a 1D problem. Okay? And how do we solve a 1D problem? So it's a minimizing f of alpha. How do we solve it? Can solve by 1D Newton. Because in 1D Newton, we don't need to use Hessian, right? So what we will use actually is alpha, but in this small 1D finding problem, let's use a different symbol for iteration number. So let's use m. So m is iteration number of the 1D line search. Okay, so this and our variable is alpha, right? Our new variable alpha m plus 1 equals to alpha m minus f prime of alpha m over f double prime of alpha m. This is the 1D Newton, right? But the variable now is alpha and our iteration number is m. Okay? And when you, after that, when you, finally you will get a optimal, right? When you get the optimal, what do? You send back. When you get the optimal, you will send back to here. Send back. And continue with your original process. So this is how steepest descent work. And I know this is a little complicated, so let me write it down in a flow chart. Okay, let me show you in the flow chart. So flow chart of steepest descent. So initially, I have a vector of x k equals to 0 and k equals to 0. Same as Newton's method. And then you need to, of course, calculate your gradient. This is, of course, you must do, okay? But you don't need to calculate the Hessian. Next, you introduce the new equation okay? But you don't know so far this is unknown. Okay? So what do? We will solve a smaller problem to find alpha. So the small problem is like this. Let me write down in this way. So this let me call this a sub problem. So this is originally the main problem. This is the main problem. Okay, so we have like a main problem and a sub-problem. Okay, so in the main problem, we are minimizing f of x. And in the sub-problem, we are minimizing also f, but the variable is only alpha. Okay, so initially, we will also have an initial guess. So alpha n equals to 0, and n is 0 at this point. So how do you get alpha n equals to 0? It's up to you. You can just guess, okay? Because you don't know what's the solution. So I should do this. I should get rid of this. The process should be going this way. When you complete calculation, you don't go down first. You go to the sub-problem. You try to solve this. And over here, sorry. The process should be like this, and then you go this way. Okay. And over here, where f alpha is alpha. So you use this to plug in. To plug in f. You plug in. Okay? And inside, because you have a variable of alpha, so this become a function of alpha. Okay? Okay. So once you have that, initially you make a guess of alpha, and also your iteration number n equals to 0. Then you move on to the next stage is alpha m plus 1 equals to alpha m minus f prime of alpha m over f double prime of alpha m. You solve for this, and then you, of course, you do convergence check. So if yes, then you have your optimal alpha, which will be your last alpha. And if no, you need to go back to here. If not yet converge, and of course when you move on, m equals to m plus 1. Okay? So when you have your optimal alpha, you need to go back and plug in. So plug in. Okay, now you have your new x. Now you have your solution because you know alpha when you solve for this subproblem. Then you could plug in. And when you plug in, you have your new point. You over here can do your convergence check again. But it's checking what? Checking this and this. Over on the right hand side in the subproblem, when you do the convergence check, you are checking this and this. Right? Different. This is checking of alpha. This is checking of x. Okay, so different. Okay? When you do the convergence check, if yes, then your optimal X will be your last design. If no, then you need to go to here. And of course, K equals to K plus 1. Okay, so that's the flow chart. So the main body is this flow. But over here, in order to solve for alpha, you go out to operate this subproblem, and then you come back. Okay? So, any question? I will try to solve a problem right now, so you won't be confused. Any question right now? Okay, let me show you. So one example. Let's solve a 2D problem. Trying to minimize f equals to x1 squared plus 5x2 squared. Just a very simple one. So supposedly the solution is 0 and 0. Okay? And let's start with initial guess. Let me just make it simple. So the initial guess xk equals 0. Let's say 3, 3. And k equals to 0. Okay, that's my guess. So what's next? I need to check the gradient. The gradient will be 2x1 and 10x2. Okay, so based on steepest descent, my x1 should equals to x0 minus some alpha times my gradient 0. So let me plug in. This is my 3, 3. This is some value I don't know, alpha 0. And my gradient will be 6 and 30. Okay, so I actually have something like this. 3 minus 6 alpha 0. 3 minus 30 alpha 0. Okay, so now I need to move to my subproblem. So over here, my subproblem. So my f become what? I plug in. So basically 3 minus 6 alpha square plus 5, 3 minus 30 alpha square. So I truly derive this. No, I'm not going to derive this. Just because for solving this, I don't need to expand it. I can still solve in this form. Now, I need to have my initial alpha 0. So let's make a guess. 1. I don't know. So my iteration number m equals 0. And for 1D Newton, I'm using the line search, right? For 1D Newton, I need to do first derivative, which will be 6 minus 12 alpha plus multiplied by 10, 30 minus 300 alpha, right? And this will give me 36 minus 312 alpha. So my f double prom will be minus 312. Okay, so 1D Newton tell me I should have 1 minus 36 minus 312 times, my initial guess is 1 over minus 312. So let me quickly use MATLAB I'm lazy, I'm just using MATLAB to get the number. You can use calculator. 1 minus 32 minus 312 over minus 312. So I get some number 0.1154. Okay, so for the convergence check, of course, the first one and the second one, the difference definitely larger than 10 to the power of negative 3. So I need to do it again. So now m equals to m plus 1. M now is 1. And then I do alpha. Oh, sorry, it's not a vector. Alpha is not a vector. Alpha is just a value. Alpha is not a vector, just a value. Okay, continue in my second iteration. So this will be my first iteration. And here's my second iteration. Okay, let me continue. Alpha 2 equals to the first one. First one is right here, 0.1154 minus, my gradient is here, 33 minus 312 times 0.1154 over my second order derivative minus 312. So let me use MATLAB again. 0.1154 minus 36 minus 312 times 0.1154 over negative 312. I get exactly same number. No surprise, because this is Newton's method. Newton's method can get solution in 2 iterations. So the convergence check tells you, oh, this is 0. So my optimal should be the last solution, which is 0.1154. Now I can plug in, send it back. So what would be my x1? 6 times 0.1154, 3 minus 30 times 0.1154. So I'm using MATLAB again. 3 minus 6 times 0.1154 is 2.3076. 3 minus 30 times 0.1154, negative 0.4620. Okay, so if I do the convergence check, I do a norm of x1 minus x0. So I need to calculate the distance of this. So to here I need to minus 3. So the difference between here minus 3. Okay. So here I should have 0.6924, and here I have positive 3.4620. Is it right? No, negative. So how do I get these two? This guy minus this guy, right? 2.3 something minus 3, that's negative 0.7, around 0.7. 0.4, negative 0.4 minus 3, you should get negative around 3.4 something. Yeah. So what's the norm? 0.6924 and 3.4620. So the norm, the distance, the length of this error vector is 3.5306 is of course larger than 10 to the negative 3. So my iteration number k must be plus in 1, which is 1. And then I do it again. So this was my first iteration of Steepest descent. And now this becomes my second iteration. So in my second iteration, I should do x2 equals to x1 minus a new number alpha times gradient f at 1. And so on. Keep doing the same process until I'm satisfied. Okay? So that's basically it. I'm not going to solve for another iteration because it's taking a while. Okay? Let me see. Someone asked questions. I made a mistake in derivative. Let me see. Really? Where? 指数 Why you don't use chain rule? Oh, the chain rule. I forgot about the chain rule. You're right. There are some coefficients wrong. So the chain rules, I should multiply by -6. And here I should multiply by -30. Right? Is that right? Right? So I made a mistake. That's my bad. But how come I still get a good answer? Maybe I was just lucky. Okay, let me quickly fix this. So -36, -900. So this should be -936. Okay, so over here should have 72 plus 9000. So I should have a plus 9072 alpha. So here I should have 9072. Is this correct? Is this correct? Okay, I hope it's correct. So over here, let me just get rid of this. I should have okay, and what's the answer? So I have 0.1032. Okay, so again, not yet converge. So I should recalculate those. So previous one is like this. Minus f prime is over here. Over this guy, and let's see if that's still the same answer. Yes, still the same answer. Okay, good. So this should be 1032. So over here Let me get rid of those. Did I make any mistakes so far? Please check for me. I often make mistakes like this. So if you see any mistakes, please let me know. Okay, so this is how it should look like. Do you have reference? Oh, hold on. For the second iteration of k, do we need to find another value of a of alpha, or just no? In the second iteration, you need to solve for a again, a different different alpha. So every time the line search is different, it's a separate process. So you need to do it again and again. I know it's taking a lot of time, but at least you don't need to do inverse of Hessian. Okay, that's the only good thing about this. You don't need to do Hessian. Okay, let me correct this. And let me check the norm. The norm should be the norm is 3.1573. Okay. So this will be different from previous alpha, a different alpha. Okay. Okay. So any questions? Any questions? I hope there's no more mistake. There still could be mistakes. When you do your homework, please be careful. I know it could make a lot of mistakes. Okay. Sorry, someone called me, so being interrupted. So let me share the screen again. Okay. Okay, so can you any other questions? So basically in your homework, you try to use this to find the optimal. Okay? I give you some time to think about this. If there's no problem, then that's everything I want to cover for today. That's everything. So the homework, let me mention again. The homework is right here. You solve for this problem. First, you use Newton. Second, you use Steepest. Stop calling me. Sorry, someone called me again. Okay, first one, use Newton's method. Second one, use steepest descent. And for steepest descent, just do 3 iterations. From the example I show you, you can tell it doesn't converge very fast. Initially, you are at 3.3. Later on, you are at 2.3 and minus something. So you are moving slowly. And let me draw a figure to explain what happened. Okay? So let's take a look at this function and then let me try to explain to you what happened. And I wish you could learn from my explanation right here. So if we look at a 2D drawing like this, here is x1, here is x2, and supposedly the contour should look like this, right? Just to double check, let me use MATLAB to draw it. Easy contour x1 squared plus 5 times x2 squared. Hold on, give me a second. Just double checking. Okay, yes. My computer is almost out of memory, so let me make it fast. So the contour look like this. It's actually a bunch of ellipse. A bunch of ellipse. And of course we know this is the solution, right? This is the optimal. But when we start at, for example, 3.3, 3.3 may be somewhere here. So let's say this is 3.3. And since this is an ellipse, it's not circular. So the gradient direction is around this direction. And it's like you're drawing a line. This is the gradient direction. And the dashed line is the negative gradient direction. Okay, so when you are doing this, what does that mean? That means you are trying to find a solution along this line. And you are trying to find where is the point on the line which gives you the lowest value of f. And what you found actually was somewhere over here. So if you try to visualize along this direction from the side, you will tell actually it looks like this. And this is where you have the lowest value of f if you visualize this whole thing from the side. So you are just like making a cut of this ball shape contour, and then along the cut there is a lowest point. Okay, and finding f is just to find what's the lowest point along that cut. And when you calculate alpha, you basically determine what's the proper value of alpha so that you can move from here to here. Okay, that's exactly what you have done. So after one iteration, you have this, and what will happen in the next iteration? You will try to determine what will be the gradient. So you will then realize the gradient of this point is going this way, and you should be moving along negative gradient direction. And along that direction, you will try to find the lowest point. You probably will get somewhere over here. And did you realize you will be moving zigzagging? Do you know what the zigzag mean? You will be moving like this. If like this. Okay? But I'm just exaggerating so that you understand. You are moving like this. So eventually you wish later on you find the solution. That's why it takes more iteration. Okay, so I think not this week, next week, I will try to show you how to solve these problems by computers. And I can use MATLAB to plot out the process. So then by that time, you can easily understand what's going on. Okay? So if you still have